I will continue with the topic of interference of light waves. In my last lecture, I had stopped at describing the some form of interference pattern that comes in, and then I spoke about the blurring of interference, and we saw that the laser parameters are such that a laser is ideal for creating interference patterns, okay, because it is coherent and also it can be made almost monochromatic. So, that is how laser becomes an ideal candidate for creating interference pattern. Okay. So, we go ahead today with a few more types of interferences, and along with that I will give you some examples where such interference is used. Okay. So, start off today with the Mach-Zehnder interferometer. Okay. So, it is something like the Michelson's interferometer itself. The interference of rays lead to patterns similar to the pattern observed in a Michelson's interferometer. If a cell Q here, Q containing a gas or a substance with a refractive index other than unity is placed here, then the interference pattern changes. Okay. So, and we want to detect that change itself of the interference pattern. Otherwise, the rest of the thing is something like a Michelson's interferometer. That is what I am trying to state here. And what is the use of detecting such an interference pattern? Okay. It gives you some idea of the substance that is there in this cell Q. So, it will give you, this makes it possible to study physics properties involving the change in refractive index. Okay. So, that is an important part of any experimental technique. So, what do we do here in the Mach-Zehnder interferometer? I have a source of light here, which is of course a laser, and it is going through here. P1 and P2 here are the transparent plates, transparent because it passes the light and part of it gets reflected also. So, they could be, it is something like a beam splitter. So, it splits this beam into this part and this part. So, splitting the beam into this two part is like division of amplitude. That is what we saw last time, division of amplitude, and Michelson's interferometer is a good example where division of amplitude takes place. So, here we are dividing the amplitude of the electric field that is associated with this light into this and to this. Of course, we are dealing with the intensity, which is square of the amplitude of the electric field. So, here is this one more beam, here is the second beam, and both of them are from the same source. So, obviously, they will give a good interference pattern, and it is a coherent light source, which is a laser. So, you will get a interference pattern, a good interference pattern. So, it is reflected again from this mirror A2 and A1. So, this beam gets reflected by A1 and this beam gets reflected by A2. Okay. The beam that gets reflected by A1, it is here. This path has not been disturbed by any other element, while this path has been, in a sense, a disturbance is brought in. This is a transparent material, transparent to this particular wavelength of light. It allows it to pass through, but then it has a refractive index and it will give a phase change which is different from this. In any case, following two paths, there is a phase change, phase difference between these two beams. In addition to that, you have one more element here which is adding to that phase difference. Okay. And that is exactly what we are going to measure. Okay. So, suppose this Q was not there, this cell wasn't there. So, it was a plane beam here, here, and I will get an interference pattern here, because these two waves combine. I can get even an interference pattern here, because P is a transparent plate. So, part of it goes here and part of it goes here. In both places I will get an interference pattern if I keep a detector here or keep a screen here. I will see the interference pattern. Okay, this is a screen. Now, so now I introduce this element here, Q cell, which can be filled with almost anything you like. And the moment this is introduced, you will see a change in the interference pattern. And it is that change in the interference pattern which you are trying to measure. And if you measure that change, you will get an idea of what is there in that cell Q. The relative refractive index can be measured to a high degree of accuracy in terms of the path of the light ray in the cell. Okay, so, if I say I get an interference pattern like this, so many lines, just as an example, this is my interference pattern which is there without the cell Q. Then I must, once the cell Q is placed in it, this interference pattern may not look like this. It may have shifted, if you can see. It has shifted by a certain amount, either on this side or that side, or some of the distances between these two may have changed, they may have come closer. So, basically the two interference patterns are same, and this relative change in interference pattern definitely is due to the substance in that cell Q. So, it could be a gas, or it could be any other substance, a gel like or solid or anything, any substance. Gas is just an idea. So, it could be that. So, from that change in the interference pattern, you can calculate back, okay? You can calculate back and find out what is delta. Delta is the phase change. So, what is the delta brought about by this cell Q? Okay. Once you know what is the delta brought about by this cell Q, you can relate it to the refractive index of the substance in that Q. Okay. So, refractive index in NQ. Now, from the refractive index you can do many other calculations. Suppose it is filled with gas, okay, and with the density of the gas your refractive index will change. So, you get the change in the refractive index, and from that you can back calculate the density of the gas inside that cell, and many such things. So, basically you are recording the interference pattern, and from that you are judging what is delta, phase change. From that you can judge what is the path difference between these two, the two rays, okay. And from that you are getting many of the properties inside this Q cell. And this is a very accurate measurement, because the interference pattern is, if you get very sharp interference patterns, it is a very accurate determination of the change in the refractive index. Okay. So, accuracy is the key here. So, this was one example of amplitude division. Amplitude division, interference pattern produced due to amplitude division. It is used, and very often Mach-Zehnder interferometer is used in many experimental cases in a laboratory, and even in industry, it is a standard procedure. And now that you have a laser which is a handy tool. You can easily get interference patterns, and so Mach-Zehnder interferometer has become a handy tool for making accurate measurements like this. Okay. So, now I will go on to two beam interference through wavefront splitting. So, I had described amplitude splitting. Now, I will describe the interference pattern and the conditions that are required to get an interference pattern from two beams which are created by division of wavefront. Okay. So, before that, I think you should just recollect what is Huygens principle. I have just written it here. If the wavefront of a light wave is known at a certain instant of time, the position of the wavefront is determined after a time delta t by considering each point of the wavefront as a source of spherical waves, and by considering spheres of radius c delta t. C is the velocity of light, delta t is the distance. So, the radius will be the velocity into the time, okay. Velocity about the source. The surface enveloping the secondary spherical wave represents the wavefront after an interval delta t. So, we must always keep this Huygens principles at the back of our mind. So, here I have just illustrated it the same Huygens principle in a picture. So, this is my point source. This has this is the wavefront, okay, of this point source. This is the next wavefront of the same point source. But then each of these points on this wavefront will create these secondary wavefronts, okay, which are shown by these semicircles here. Okay. So, then we have to find the interference between, say, this wavefront and this wavefront, this wavefront and this wavefront. Okay. So, we are really splitting this wavefront into these so many wavefronts and then checking out on the interference pattern. Okay. Here I have just written c delta t. After a time c delta t, this wavefront will be here, and these are all those little wavefronts that have been created after a time t. After a time t, and after this wavefront has travelled a distance c delta t. So, the best example is, of course, the Young's double slit interferometer. So, in accordance with Huygens principle, slits A1 and A2 can be treated as sources of waves. These sources are generated by the same primary wave and are therefore mutually coherent. Interference is observed between the waves generated by them. Okay. So, that is exactly what I have explained here. Interference is generated by these waves. So, this Young's two-slit interferometer, remember in some of the first few lectures I had introduced to you in order to explain spatial coherence. Okay. So, this is a fine example of spatial coherence. Okay. So, let me you will understand that there I had just given you an introduction to spatial coherence, and I had referred to Young's double slit interferometer. Here I will just go into a little more detail, and that will give you a better understanding. So, I have the source of light here, okay, and it splits into, and this is a plain board with two slits here and here, or two holes, whatever you like. So, there are wavefronts like this created by the source, wavefronts like this, and one of those wavefronts comes onto this slit. Okay. And from here you get these secondary wavefronts, which are these. From this, this slit also you get those secondary wave fronts. And all those secondary wave fronts begin to interfere, and if you put a screen here at a distance say L, you are going to get interference fringes. Okay. So, let us go through a little bit of mathematics of this. Okay. So, the distance between these two is fixed, you can't change it. Okay. And now we will see under what conditions can we get an interference pattern and what kind of interference pattern is that. One thing is clear, since you will definitely get an interference pattern, because as you remember these two sources are coherent. There is a correlation between this wavefront and say this wavefront. Okay. So, let us see what other conditions are needed. Okay, here I have just repeated the diagram here just to give you an idea. The path length S2y, that means from here to here, S2y is root of L square plus y plus d by 2 whole square. That it is a geometric way you can describe it. See, this is L. So, if you take this right angled triangle, then a square plus b square is the hypotenuse square. So, this is basically derived from that. Okay. D by 2, d is the distance between the two slits, and d by 2 is just this part from here to here. Okay, that is d by 2. So, geometrically you can see from the diagram S2y is given by this, and S1y, okay, S2y was this, S1y is this, y is just this point here. Okay. So, the path length of S1y is given by root of L square plus y minus d by 2 whole square. Again you have another right angle triangle, okay, and a square plus b square is equal to hypotenuse square. You are using that same formula. So, just from this geometry itself you can get this path difference. Now, the path difference is S2y minus S1y. We are always looking for the path difference. So, this thing minus this. Okay. Now, for d much less than L, d is the distance between the two slits, and this distance is quite large, which is often the case in case of any interference pattern. These two are very close. We can just expand this. You are using a binomial series expansion. So, I just expand this into this is equal to L, a little bit of algebra here, 1 plus y plus d by 2 upon 2L square. Okay. Similarly, for this, this quantity is going to look the same, only this minus sign is a bit different. So, this will give you this quantity. Okay. So, if you just minus this from this, we can obtain delta, which is the path difference, which is this minus this. Path difference comes out to be dy by L. Okay. So, here is this y is this point. This distance is y. That means the center point here, center point of the between the two slits on the screen, and the distance at which you are trying to measure the interference pattern or check out the intensity of the interference pattern at this point. So, y is that distance. So, okay, the path difference turns out to be delta is equal to dy by L. D here, everything is known, L is known, distance between this is known. Y is something we want to find out what exactly it is. The phase difference obviously is k into delta. Okay. Phase difference between the rays is delta is equal to 2 pi delta upon lambda, k into this capital delta, and k is 2 pi by lambda. So, this is the phase difference. Small delta is the phase difference and capital delta is the path difference. So, this is equal to 2 pi d upon lambda L into y. So, now we have seen this, this equation before in my previous lectures. You have seen that intensity is given by 2 I 0, which is the initial intensity, 1 plus cos delta. Okay. So, the intensity at different points of this y, I y, is equal to 2 I 0, 1 minus cos of delta means this whole thing. This whole thing I have just placed here, and y. Okay. So, this I y gives you a distribution of this intensity pattern. So, once you know the phase difference between the two path lengths, you know you can very well come to the answer to the distribution pattern of that interference pattern. So, obviously, the distribution pattern, as you can see, if there is a cos term, obviously there will be some undulation. You will have these gaps in between, dark spaces, light spaces, dark spaces, light spaces. So, whenever you have this term, this will occur. Now, just see at this point, at O, if you see this interference, at O means y is equal to 0. Okay. So, we want to see what is the intensity looks like at this point O. So, y is equal to 0 here. So, it is cos 0. Cos 0 is 1. 1 plus 1, 2. 2 into 2 is 4. Okay. So, I y becomes 4 I 0. I 0 was the intensity when we started off with. Okay. So, I 0 was the intensity of these beams initial. Okay. So, you are going to get a 4 I 0, that means you are going to get a maximum intensity here. So, you will get a bright spot. The next spot, the next distance y, cos may not be 0, it will be something in between. This will be a dark space. Similarly, the next y, it will be a bright, dark, bright, dark. So, obviously, you get an intensity pattern here. Okay. So, that is how it goes all along that screen. So, with this path difference, I am getting this interference pattern. Now, try to recollect what I had tried to tell you at that time about the coherence, spatial coherence. Okay. So, the moment there is spatial coherence, I will get the interference pattern. That is what I had explained before. If there is no spatial coherence, then I will not get the interference pattern. Okay, it will be blurred. So, it was the spatial coherence was, these wave fronts that I had shown. So, and the smaller wave fronts that are coming out here. So, are these two wave fronts correlated with each other or not? That is the question. If they are, then you will get the interference pattern. If they aren't, then you do not get an interference pattern. Okay. So, suppose you had two sources instead of this one source. These two sources, and you checked on the interference pattern, most likely you will not get an interference pattern because they may not be coherent at all. Taking it from a single source ensures that it is coherent, and taking it with a laser source, you can just relax, you can be definite that these two are correlated very well. The coherence, the spatial coherence is very good. Okay. So, suppose I were to take two lasers, two separate lasers, okay, with a different wavelength, you may not see that interference pattern. Okay. See, you may not see because See here it is the phase is related to the wavelength here. Okay. So, here I have assumed the assumption is the light that is here, it is nearly monochromatic, it has only one wavelength. The moment you have two different wavelengths, there will be blurring of these images. Okay. So, that is one of the conditions of the interference. Not that you do not get an interference with two different wavelengths, the correlations have to be good or the wavelengths have to be very close to each other, so that the correlation or the coherence lengths are followed. So, all those conditions will come into the picture. Okay. So, your phase difference actually gives you some idea of the wavelength that you need to take. Okay. So, if you have an interference pattern, it is giving you some idea of the wavelength also that has been used here. Okay. And quite often from the interference pattern you do get an idea of the wavelength of the light that has been used. Okay. So, the phase difference between two beams of light or the path difference between the two beams of light locks in a lot of information about that beam of light. Okay. We will continue further with the interference in my next lecture. Actually, the interference topic is very interesting, and it is used in many areas of experimental techniques.